Okay, a few announcements, and then we'll jump right into it today. So Unit 8, if you forgot and didn't take the Unit 8 test, I'm reopening it today through the weekend. Not looking in any particular direction.
Wait, did you actually forget Winston?
No.
Oh, good job. I'm proud of you.
No, he just
No,
didn't
wait,
do it.
sorry, what did you say?
Did you forget to do it?
Oh, yeah.
I think we should have made a contract this time.
I know.
Yeah.
Okay, if Winston forgets to take the AP test, bring us all donuts. And if he remembers to take the
That
AP
shouldn't be a
test,
problem.
I'm pretty sure his mom
Love
actually
donuts.
like
Yeah,
slots.
there'd be some bigger problems.
Yeah.
Okay, so if you didn't yet, it will be open through the weekend to take. Please take it so your two tests don't overlap with each other.
Okay.
Now, what I decided to do in terms of corrections and retakes for Unit 8 is we're going to put pause on it for just a little bit. Because Unit 9 is so short in the time we're spending on it, I don't want to take your focus away from it, because once again, like, we're spending today and next time and then we're testing. So we're going to hold off on retaking the Unit 8 until after spring break, okay? So I'm not even going to post it. If you want to do corrections because you're bored, you can.
I'm so bored. I'm
Hey, no,
I mean, maybe if you're stuck at grandma's house.
Yeah.
so.
And she's regretted something.
But otherwise, don't worry about it for now, okay?
Yeah. Grandma's fed you too much of the meeting, can't do it.
Okay, I think that's it. Just a heads up, so next Friday, right, we'll be taking the Unit 9 test in class. If you're not here or won't be here because you're headed off on spring break earlier things, it will be available online as always, because there's some kids who never are with us in person. I just highly recommend that if you are leaving early, you take it before you leave, right? Don't wait till after spring break to take the test. After spring break, all we want to do is then just review everything. We don't want to worry about past stuff besides like correcting certain things. So, okay, go to your notes from last time. We had a few little things to finish up before we transition into days.
What day is the AP test on?
May 2nd.
Aha, same. That's like. I have 2 AP tests on.
Yes, so I did send an email out to all of you and your parents about the AP test. Give me your attention here, please.
Stop.
So our test is scheduled to take in school on May 7th. That was our original day. Anyways, that's the day I've been planning on all year. If by chance you already know you aren't going to be able to take it that day, like for extracurricular reasons, like you have something else going on or whatever, I need to know as soon as possible, because you can take it the next time around, but that's not till May 25th. Which, yeah, could be beneficial, but I found sometimes more time isn't always better for a student, especially when summer starts rolling around.
Okay.
But if that is the case, there is a second day to take it, and there is a third day to take it at home online in June, if by chance, but I assume all of you are here in person, so you're going to take it in person. So.
Do you have to like record your screen while you do that? So you're not cheating or something?
They have all sorts of like
Yeah, they
things
have
set up.
Yeah.
Yeah.
And if you cheat, man, like, and they catch you, it's bad stuff, dude. Like, I read the book. You do not want to get caught cheating.
So last
Like,
year I
yeah.
took an AP world
Like last
test, and I think what they did is they put it in full screen mode, so you can access the tabs.
And I can't access just a separate laptop that's
No way, it's just
sitting
impossible.
right there.
Yeah, you just kind of. Well,
Yeah.
most people wouldn't have one.
Not saying I cheat, jeez.
Well, at that point,
Honestly,
it's
from
like,
my
what can
experience
you
with
do?
AP Chemistry, with how it's timed,
You
you
can't.
don't have time. Because last year for AP Chemistry, you could use whatever resources you wanted. You could Google it all. It's not going to help you, though, in the time that's given and the way they write the questions. They're just so good at writing questions that have never been seen or before. So, but
Okay, wait. What time of day is it?
8 a.m.
So what are you testing?
So like, how would that day?
So pretty much on the day of the AP test, you guys will just be excused from all your classes to take the test.
What? How long is all of our classes?
So yeah, especially with our shortened schedule, It's a B day, so one of those.
So according to your
So multiple choice is an hour and a half,
my AP test that day.
and then you get
What's your other-
10-minute break or something, and then the free response is an hour and 45 minutes.
Sheesh, that's gonna be.
It's a
like-
long
So getting excused
test.
from all your
But then,
classes.
after you're done, you're all gonna come back here and I'll have pizza for you.
Yay!
Oh, sorry, score.
Do you have a test right after?
Yeah, I have the test the same day.
We'll save you some.
Damn.
We'll save you a box for when they're done. I know I feel so bad when people have
Wait,
back-to-back
where are you getting
tests.
your
Like, how does that happen? The two tests that I happen to be taking are the two tests that are on the same
On the
day.
same
Okay.
day.
When are we gonna have our AP class? We have like the day after test?
I don't know, yeah, just,
Wait,
I
are
don't
we
know.
gonna
I
do
got a
that?
list of things after the test. It doesn't matter what we're doing.
Chemistry awesome course.
After the test, okay? You gotta figure that out.
It'll help us review.
Oh.
We would have to come up with it, that's like.
Me and Gavin will get excused from our first two periods.
Okay.
Set it up.
Before we start talking about what we're gonna do after the test, we gotta get there first, right? Okay, so
What if we just want to?
everyone close your mouths, think to yourself, don't say it out loud. Okay, so one key phrase that you need to understand with Unit 9, because it's really the theme of all of it, is what we mean by saying that a reaction is thermodynamically favored. Okay, so from last time's lesson, see if you can come up with a definition in your head of what do I mean when I say a process is thermodynamically favored. Don't say it out loud, just think in your head for a second. You can look over your notes if you need to. Let's make sure we have a really good foundation of what that means. Okay, raise a hand, anyone willing to share? Evan.
It becomes less dispersed on its own, like naturally, without us having to do something.
Ooh, really, really close.
But you're
Is
not
there-
quite
The
there.
right track.
You're on the right track.
How about
But
slide
you're wrong.
So,
I didn't want to break the silence.
the piece that you're missing, Evan,
Mm-hmm.
and I'm glad you bring this up though, because you're talking primarily about entropy, right? And it is true that entropy naturally gets more dispersed, right? The second law of thermodynamics states that the world is going to chaos, pretty much. Okay? Because
Which is
things just
true.
are getting more dispersed and more spread out. But there are some processes that are thermodynamically favored where things do get more organized. So that's where we have the other component of enthalpy that plays into it as well. So that's like, I guess, part of it, but not all of it.
Okay.
So what else can we add to Evan's explanation? What it means when something is thermodynamically favored.
Maybe like it'll naturally complete a reaction without any extra work. Maybe like there's a certain temperature, maybe like room temperature or something, where
Perfect.
it says it'll complete the reaction on its own.
Good. Have a smiley face, Sajid. Well said. Yeah, thermodynamically favored processes don't require external work done to them. They don't need heat. I mean, once again, at a given temperature, but they don't need heat. You don't have to plug them in. They just go and put energy out. That's the other big theme. Is all thermodynamically favored processes have a negative delta G, meaning the Gibbs free energy is being released in the process. Okay? So just recapping last time, and this goes along actually a lot with what Evan brought up, is we talked about how delta S, which is entropy, and delta H, which is enthalpy, play together to whether something or not is thermodynamically favored. Right? We went through this table of if this is positive and this is negative, what the cases are. So in this problem where we ended last time, the first thing we did is we wanted to predict the direction in which delta G for the reaction if the temperature is increasing. So what we knew, I'm just recapping here to remind our brains what's going on. So we have this equation, so delta H minus T delta S. Okay, for this reaction, we knew that it was exothermic, so delta H was negative. We also knew that the enthalpy was negative. How did I know that? Entropy, sorry.
Because it goes from 4 to 2.
Good, so we're looking at the equation, right, of what happens. So 4 molecules to 2 means it's getting more organized, less entropy. And so if I want this to be negative, right, it's kind of what we're saying, right? So it's saying temperature is going up. So the higher the temperature gets, the less likely it is to be negative, right? Because you're adding a bigger positive number to it. The second one here now is just the math side of things. Let's say more likely to be like an FRQ question where we would just plug in this and this, minus we do have to be very cautious with units here. Anyone see the problem with our units?
Kilojoules and joules per Kelvin.
Yeah, so one of them is in kilojoules and the other is in joules. And then we also have to make sure the temperature is in Kelvin. Okay, so let's just do this one real quick. So we have delta G equals, any preference, you want to go to joules or kilojoules?
Kilojoules.
No, I think going to joules, like, yeah, kilojoules is easy.
Okay, so we're going to keep the delta H as is. Okay. Minus, how do I get from Celsius to Kelvin?
Plus 274.
Oh,
Three.
so close. 273.
You failed, man.
No, I said 3 right after. I knew, okay, sometimes we say.
I'm joking.
Stop it.
That's
Stop
on
it.
your formula sheet, by the way, that conversion.
So
Okay.
you don't even need to know it.
Ha, Taylor.
But that doesn't mean that you
And
should.
then I'm going to change this one into kilojoules. So I'm going to move the decimal 1, 2, 3. This is joules per Kelvin.
Alright, here we go, graphing
Okay.
calculator time.
It's like,
What
did it
that
really go
is?
down?
What?
I'm honestly not sure.
Yeah, Zach.
Shouldn't it be kilojoules per Kelvin?
Oh, thank you. I changed it, but I didn't change my unit. Did anyone type this in yet?
I think I got negative one. But I don't know if we did that. Oh, it's time for negative, nope. Okay, wait, so I'll take that plus.
Man, why is that again?
So I got negative.
Negative 32.
Yeah, that's right.
Give a second witness to that number.
I counted it wrong, but that's-
Negative 33.286.
Ha, you were off by 1 also.
Yeah.
How did I manage that? What, how did I plug a number in wrong?
Yeah.
98.19.
How many decimal? I get 1, no, I only get 2 actually.
Wait, no, I plugged that in right.
Wait. Wow.
92.3, oh, I didn't get the plug. Okay, that makes sense.
What would my unit be on this number?
Kilojoules.
Good, Evan.
Kilojoules per
Right, because the kelvins cancel, so it's just kilojoules, which makes sense for a unit of energy, right?
I feel like it should be kilojoules squared, but that's just me.
That does make, I was thinking
You know what's
about
weird to
that.
Because
think
you're
about?
minusing, not timesing.
So for acceleration, you do seconds squared.
Wait.
But
Yeah.
like, why is a second squared? Like, think about it, because time is just like a two-dimensional thing. So once you square it, or one-dimensional, depending on how you look at it. Once you square it, it's like multiple times.
Whoa.
Jar.
I don't know if I'm gonna be able to answer that one, but let's put it in the jar. I get perplexed by that myself. Oh, I almost ripped his eyeball off.
Imagine Taylor transfers out and then we're reading this small case and we just see like.
Yeah, then it gets a bunch of stepping of others, like, yeah, then you're cubing it, so. Okay, questions on this equation? Okay, last 2 little things dealing with Gibbs free energy before we transition a little bit, okay, is some reactions or processes can be thermodynamically favored, meaning they should happen on their own accord, but they're stuck under what we call this thing known as kinetic control. Kinetic control often is because of a too high of activation energy. What's activation energy?
It's like the first part, it's like the,
It's
it's
Did I see
that.
everyone's like drawing hills on like this,
It's that.
right? So it's the energy it takes to get it to go. This could be thermodynamically favored, but it needs a spark to get it to proceed. Combustions are a great example, right? A combustion reaction, once you spark a fire,
it goes.
it's just gonna keep going on its own. It's thermodynamically favored. But without getting that spark, it's under what we call kinetic control and that it's stuck. So just kind of a vocabulary word to be afraid of, be aware of.
Yeah.
Maybe.
I only goes to chemistry class. Kinetic control.
Now, we have another equation here with delta G that
You're
actually
scared of
helps
the
us
ghost of
relate.
Christmas past?
No, the Ghost of Christmas future is scary though, okay? No one can argue with that. That thing is scary.
I know, but
Scary.
why are you
Christmas
scared
future?
of the ghost of
No, the
Christmas
Ghost of
past?
Christmas.
She was saying scary, and then you go, I am the ghost of chemistry past.
Well, because chemistry past is scary, man. Thing is, chemistry future will know more, but chemistry past we didn't know anything.
But in the
I'll go.
Oh, I know, how much happened over there.
Like that idea.
Okay, so this equation here on our formula sheet, I'll explain. Okay, this relates gives free energy to equilibrium. Okay,
Wait, what letter is
so
That's
I'm
right.
gonna explain my cursor here. So this is ln, the natural
Oh, I was
log.
right. Natural log.
I always learn to write natural log in cursive.
It's
Maybe-
in the circle.
Oh, the equation's right in the circle. Thank you, guys.
unfortunate?
I don't even know how to do it.
I just, if you write a normal like ln, I don't know. That's just how I learned it.
She's fancy.
I'll just write bold because I'm gonna look back at my notes. and
You just do
not
what
know
you've
that
been taught, right? That's how I was taught, so I continue doing it.
My sweater.
So R here, everybody, is actually the gas constant
I should leave that sign.
way back when from PV equals nRT.
Whoa.
Now the units, if you look here on your paper, if you have your formula sheet handy, right, because there's different values for R. One of the values of R we never used when we were dealing with pressure, because that unit of R had a value of joules in it. This is where it now is used. Okay? T is temperature, and then K is your equilibrium constant. So what we're looking at here is that if delta G is negative, we said that means that the reaction is favored, right? It's thermodynamically favored when delta G is negative, because that's how much free energy is being released. In terms of an equilibrium constant, just as a reminder, K is the ratio of products over reactants. Any thoughts on what that would tell me about my K value?
It's less than 0. Wait.
It's higher because it's negative.
Good. So delta G is negative. That means it's thermodynamically favored, right? First off, some of you are on the right track. K is never going to be positive or negative. I mean, it's always positive. It's never going to be negative because it's just a ratio. But if something is thermodynamically favored, what part of my ratio do I have more of? Products. Because if it's happening on its own accord, it's just making products. So K will always be greater than 1 for a thermodynamically favored reaction. When it's 0, that means their system is at equilibrium.
But that doesn't actually exist.
That was the most perfect 0 ever.
Yeah, it's actually so good.
Thank you.
So
Did yours say positive here?
Yeah.
Okay, wait, I have a question. Whatever happened to like the big like ball of the projector like on the screen? Like, did that stop happening? Or
No.
do we just pretend it
That's
doesn't?
why I had to write the equation over there.
So
It's like
you just
better.
learned how to do it now.
Yeah, well, with how we move the camera now, it's on a tripod. It's always really high, so I don't hit it as often as I did before.
Okay.
Because
got it.
before it used to be like dead center.
You know, like we used to talk about it all the time,
Yeah,
and now we never
it's
talk
still
about
there.
it.
Yeah.
Okay.
Is it time?
Yeah.
Did you just
So on the one where it says we give the 0, shouldn't the K be equal to 1? Because it's like the ln of K, so the ln
Oh,
of 1.
yes, my perfect 0, I didn't mean to even write.
No.
Thank you, Zach. Yeah, so it's never going to equal 0, it's going to equal 1, because the ratio is the same. Thank you, how does my face that?
What divided by what equals 0?
And then that would be, yeah.
Yeah. No, you can do
Oh,
something.
you can't do anything divided by
Now, that equation, everybody, this
So
one,
if you don't have any products.
is on your formula sheet. But often, you know, because it's just the way they love to do things, they'll ask you to solve for K in this equation. So I just want to go through the algebra really quick to make sure we understand how to rearrange this equation for those that aren't as familiar with working with natural logs. Because the rearranged equation is not on your formula sheet. Okay, so I didn't give you as much space as I meant to right under this equation. So if you want to just like do it in that space below, you can like kind of like draw an arrow. That's you can do it then. Okay, so we're gonna rearrange this and find K by itself. So what would I do first algebraically here? Good, so I'm going to divide by negative RT.
Let's say you're right,
Okay, so now I have delta G naught over RT and it's negative equals the natural log of K. So I just rewrote my equation after dividing it over.
Wait, why can't you divide the ln with the k? Or with
Good
the-
question. So that's why I bring it up is for those that haven't learned as much about the natural log.
Oh,
So natural log is a function. It's, I'm sorry, something is
You have
buzzing
to
really loudly. And so the way that you inverse or get rid of a natural log is with the little e button. So what we're going to do is we're going to take both of these.
Just
We're going to do e to the power of that, e to the power of this. Because if you do that, it gets rid of that.
The chances of me remembering how to do that.
Is this on our formula sheet?
Don't worry, you'll learn it in
No.
junior year.
So that's, yeah, so this equation right here, everybody, is not on your formula sheet, but they may ask you to solve for just K. So your options are one, if you are comfortable with algebras, I wouldn't memorize it, because you can just do this.
yeah, that's how that works.
If not, then you could memorize that equation. But, so, questions on any of those algebra steps though?
K equals E root.
Okay.
Equals negative triangle.
Oh, that is actually kind of a good way of remembering it.
Yeah. Control the
Eager.
Eager.
Don't forget the negative.
It's like EGAD.
From Louis Expansion.
No, but I know who you're talking about.
Okay,
Some last some.
now, one other thing that I forgot to say that's important to recognize with thermodynamically favored reactions is thermodynamically favored reactions, that phrase tells us nothing about how fast or slow the reaction is going to go. Okay, speed is all about rate. Okay?
Good job.
But it has nothing to do, you can have a thermodynamically favored reaction that is very, very slow. Okay, now one way you can get something that is not favored to become favored is through this process known as a coupling. Okay, by coupling reactions together, you can get something that won't normally happen on its own to now happen on its own by doing them together or side by with each other. Often, like with their mechanisms, they're going to have common intermediates. So it's very, very similar to what we saw with Hess's law of how you can just add them together to figure out what the overall energy would be. So, but that's what it means when it talks about coupling a reaction. So, okay, any questions? There wasn't any question that people posted from the reading, but just any final questions on entropy before we transition slightly?
The do galvanic electrolytic cell.
Okay,
Dude, you
grab that
sounded
other
so
note
cool when
packet.
you said that.
I know,
You're
right?
being Star Trek or something.
The galvanic electrolytic cells have failed, bro.
Doesn't that sound like Star Trek?
When he said it like that, yeah.
I've never even watched Star Trek.
Okay, everybody stand up real quick.
Yes.
Stand up.
Wait, we should do the dance. Here we go.
You get to do the dance.
It's the dance. You gotta do the dance.
Or just stand up and stretch, one of the two.
Oh,
Some of you are just looking a little sleepy. I know it's Friday.
It's
Um,
Friday.
While while you're standing, turn to your table, buddy, and if you could have any pet in the entire world and not have to worry about like eating you and stuff like that, what would you have? Let's go to my mask. I found mints and mask a lion. Okay, how's you?
Oh,
If you like
yeah, that's a big house. You know, I feel like having a house in there, like my summer home is, you know?
They would be so excited to find so much.
Yeah, totally have a piece.
So many people have whale.
Okay,
Yeah.
here we go.
What about a sword fish?
Oh, that's a good point. Or I could just,
If you're underwater sword fighting,
or I could just go buy a sword.
and I get a fan.
What is that? That's like that weird Listerine mouthwash.
Oh, I love that stuff.
What are you saying about my breath?
Don't sweat.
I love those.
I've done it before. I actually know what it is.
No, but with a mask on, I found anything like.
Oh, that's, your
I
balls.
already took one.
Okay,
Okay,
wait, here. Gavin, hook me up.
My nose is cracked. Go on.
Okay, you have to keep your
Dude,
mouth
just
shut.
like my eyes are watering right
That
here.
turns into
I'm not gonna do it.
Okay, I'm gonna die. Ready?
What even? Wait, what do you
No.
It's just like it's just like a mint. They're just really strong.
Oh.
So strong.
Oh
It's like
yeah, I can see what you mean. It's like going into my eyes.
That's what we used to give my dog to help.
Okay,
We
here we
would put it
go.
on her tongue and she'd be like,
Focus back up front with me.
it's so
Now they're not gonna talk, because it hurts.
Oh.
Wait.
Oh,
Okay,
wait.
better keep your mouth closed.
Yeah, I can't talk to them.
Okay, so what we're going to be talking about now, everybody, is a type of thermodynamically favored process that produces electrical energy. They are known as galvanic or voltaic cells. Now, those two words they mean one and the same. We just have two words for the same thing. Okay, so just be familiar with both. But these are spontaneous reactions that do electrical work. In a sense, this is how batteries work. Now, a few background things and review things we need to cover first, okay? For a smiley face, don't say it out loud. This equation is on your paper already. It's just like right above the diagram, okay? Don't say it out loud and don't talk to your neighbor. Can you identify for me in this process what's being oxidized and what's being reduced?
Oh
It's been a
yeah.
while. Don't say it out loud. Just write it on your paper.
That's an oil rig, okay, that's a hint
That isn't it.
for all the epic people out there.
All the dean people,
Don't say that.
super gnarly,
Don't stop.
Stop.
totally legit, too legit to quit.
Tubular, dude.
Set your pencil down when you have an answer.
I think I did got that right. Yeah, I got that right. I think so, dude. I'm gonna get it wrong. I'm gonna be sad. Okay, trick question. It's opposite. Wait, I thought
I got
the
it.
C you matched up with the Z end? That was sarcastic.
Oh, I was like,
I
oh.
didn't actually think that.
Okay, if you identified that copper is being reduced and zinc is being oxidized, you can have a smiley face.
Wait.
I thought it was
I'm
Wasn't
pretty sure you're
oxide?
wrong.
I just remember.
Okay, so a lot of you remember.
Hey, I did it!
Let's
So
go.
oil means oxidation is losing electrons.
Oh, excuse me.
Reduction is gaining electrons.
Yeah, so you wrote it wrong.
What?
I think it was like
So-
backwards.
Oh,
You
yeah, I
see,
read it. I read it wrong.
Yes.
It's always like opposites. And
Yeah, it feels backwards. The charge, though, makes sense with the word reduced. Because reduced means to go down, and the charge does go down for the thing that is reduced, but it does go backwards because electrons are negative things. Okay? Now, what happens here is if I were to just put these two things together as is, okay, this process would happen and the electrons would transfer. What we can do, though, is if we separate the reaction into two different places and link it with a wire, we can get the electrons to flow through the wire and power
Your Xbox controller.
whatever we need to power.
Plug in your Xbox controller.
I have a
Oh, yeah.
transfer of electrons, what we need to understand here is really what's going on at the molecular level. So we're going to label this diagram, and the key thing is, and if you have different colors or things to help you maybe signify, is understanding all the different things that are going on at the molecular level. So this right here is what we call a voltaic cell. Okay, each beaker represents a half reaction like so. Okay, so let's label what we have and then we'll talk about what's going to happen.
Wait, saying this galvanic, voltaic, and electrolytic cells, whatever, is just saying battery. The batteries are failing. That's what you were saying.
Yeah, no, but it sounds so much cooler.
Yeah, it's
No,
the batteries are dying.
Imagine like
Yeah.
you have something and you're like, dude, could you get me some galvanic cells? And like,
Wait, yeah, that'd be kind of sick. That should be Duracell's new marketing campaign.
yeah, galvanic cells.
Okay, I'm going to label this one zinc. This is my zinc electrode, and this is my copper electrode. Once again, it doesn't matter which side you do it on, right? Okay, so what we mean by an electrode here is this is an electrode. Okay, it's a solid strip of pure zinc, solid strip of pure copper.
Which one
Now,
is blue?
the copper.
One is copper, okay, because that one.
And blue and copper.
Okay, now, if I were everybody to just place zinc in the copper, the reaction would start. So we're separating it because we want to get the electrons through the wire, not just start happening right away. So right now, they're sitting in a solution of the same chemical, so no reaction will happen. So I'm going to draw some liquid here. So the zinc is sitting in a solution of zinc nitrate, actually. The nitrate doesn't matter a whole lot. It's kind of just a spectator here. But. Okay, so this is a zinc nitrate solution. And then this, so everything I'm doing in blue is like just the setup. Okay, nothing is happening yet. Okay, and then this is copper nitrate solution. Okay, this piece right here is what we call our salt bridge. Now the salt bridge can be made of a variety of things. First off, what do we mean in chemistry when we use the word salt?
It's like
Isn't it ionic bond?
Good, ionic formula, positive, negative things. So you can make a salt bridge with any salt you want. The biggest thing is you've just got to pick a salt that won't react with the things you're trying to do, otherwise you're going to get side reactions going on. So our particular salt bridge has potassium nitrate, but it could have been NaCl or something else. Now the salt bridge just needs to be something that allows things to flow and move. So my salt bridge is literally a piece of paper, because water can flow across paper, right? You can get really fancy with these types of salt bridges.
But why? Why like not just use paper? You know what I'm saying? Paper works just fine.
It depends.
Don't know exactly, but the biggest thing is if you use one of these, you don't just pour salt water in it, because they would just come right out, right? Is you actually make like a gel solution. So it's a gel that stays inside of it.
I think paper works water.
I'll be honest, I don't know what would be your reason.
It's just cheaper.
You just shove some Marigel in there.
It's not cheaper.
Okay. Let's see, what else do we need for our set? Oh, this right here is your wire. Okay, typically the wire would be hooked up to whatever you're trying to power, or in our case, I'm just gonna hook it up to a voltmeter to measure how many volts we're making. Okay, but that's what that thing across the top is we're gonna link the two with the wire. Okay? Exactly.
So the salt bridge doesn't react with the solutions?
No.
Or,
Yeah, good note. Evan.
So is this like essentially making a battery?
Yes.
Okay, and another thing. So the first person who made a battery, I don't know if you know this, but like, did they do it like this, and did they like know the chemistry behind it, or did they just kind of like?
Were they just like, oh, electricity?
What shall we call it?
I have no idea, Evan.
I've
I've never looked into the history of a battery.
Yo, I was watching this TV show, and basically it's in the Stone Age, but this guy's a science brain, and he just totally makes a battery. It was sick.
Huh. I'll look that up. I'm curious to know too, like,
Watch it. Doctor sound, no, he's not.
Yeah, huh?
They're referring to soap.
Okay. Okay, now in pink, everybody.
If I say that.
I'm going to show once everything is connected, right? Because the biggest thing is notice with any circuit it has to be complete, right? So that's why there's the top and the bottom, so everything can flow. Okay, so in pink I'm going to draw what is happening with the changes. Okay, so here's my chemical reaction. Okay, first off we need to figure out which way are the electrons going to flow through the wire. Are they flowing from zinc to copper or copper to zinc?
Zinc to
Or
It had something to do with the oxidation.
copper to
Oh, it's not zinc.
Because which one was losing?
copper to zinc.
Okay, so oil ray, so oxidation is losing, so zinc is losing its electrons.
So it was.
Okay, so first thing I want you to label is put a little E, and then draw arrows showing it's coming across.
No, it's not Markiplier, mean.
Okay, so the electrons are flowing from zinc to copper. Now, coming back to the equation, what's happening to zinc when it loses its electrons?
It becomes positive.
Good, and positively charged things are always
Explosive.
aqueous. So what's going to happen is this zinc electrode,
Is it gonna like melt?
I don't know if the right word is melt, but yeah.
Explode.
So why didn't they explode? That'd be so much more exciting.
So the zinc electrode is literally going to start dissolving into the
Wait,
solution.
like that silver nitrate stuff.
Yes. So that one reaction that we did is, I mean, it's a redox reaction. Okay. Okay, so that's me showing that it's getting smaller. Okay, so this electrode gets smaller as the electrons leave. Alright, electrons flow through the wire, they come attached to the copper. What happens to the copper in the equation?
It gains negative.
So what's happening on this electrode?
Is it getting
It's
bigger?
sucking up the water.
Why?
So there's copper in the solution, right?
Yeah, I don't want to do it.
So the copper in the solution, because the electrons are negative, these things are positive. The positive attaches to it, becomes solid copper, and this electrode gets bigger.
Dude, that's kind of cool.
Wait, can you say that one more time?
Yeah. So as the electrons come across, the positive ions in solution attach on, take those electrons, becoming solid copper, and the electrons will get bigger.
Does this
It
like
becomes like a solid. It goes from being liquid.
Okay.
to
Yeah. I would say aqueous to solid. But yeah.
No, they're different.
Is that how those like crystal growing things work? Like they're taking, because don't you put a solution, like a little packet in the water and then you put the crystal things in? So is it that it's like attracting the negative
I don't know.
growing?
Are you talking about like when you make like rock candy type crystals? Is that what you're talking about?
No,
What
it's
about-
like the,
Is it like in the lab when we would shake it or whatever? and it would
like the
fall off?
little salt crystal things that you can grow in the water?
You know how you
I
had that
don't
video
know.
with the copper
I've never really looked into those.
The stuff with the
They
water?
could be. The other thing is it could just be it's a super saturated solution thing again, and it's just you're giving it something to latch on to, and so it comes out. That would be more likely, my guess, because I don't know what they would have to like how like it. But yeah, good question. I actually have a demo next time where we will, in a sense, kind of grow crystals, but we like force the electrons to come. So yeah, good connection.
So like, this isn't like super related, but it's some chemistry kind of.
Okay.
I'm not sure what chemistry.
Well, just go.
Okay, it's an example. So you know how like the towel can absorb water?
Yeah.
Why? Like what is it?
Wait, he has a point.
Oh, he does have. That's why I'm giving him.
Oh, okay.
He does have a point. We just don't have time to talk about it. That's a very good question.
What did you say?
Okay,
Why?
me giving you this isn't saying I don't like your question. It's saying I do like your
You're just saying you
question.
want to hear it
I
later.
want to talk
Why
about it.
do paper towels absorb?
No, it is like
Why
there's
is
so
bound
many
so much
things
more
that like
efficient?
yeah, the more chemistry you learn, the more you question like little things in life, like what the like I use this every day, but how does that even like work, right? Gavin.
So, when the thing comes out, is that like the
boggled my
One of the
mind.
reasons,
It's
yeah.
not chemistry related.
Okay, final piece, everybody. We gotta talk about that salt bridge. So the salt bridge wasn't there, this wouldn't happen. Okay? Now here's why. So we know the electrons are flowing this way, right? These are attaching on. So what's happening is, as this happens, this solution, this half cell,
Well, it becomes NO3 saturated. Or like there's
which
too much
means
NO3.
it becomes very negative.
And there's too little Zn plus on the other side, so it like goes to the other side and you become friends.
Wait,
Kinda.
what?
It makes
So
No, it doesn't.
if this side, so this, everyone understand how this is gonna become extra negative as written? Because all the positives are leaving the water, right? So the water itself would become excess negative. If this side is excess negative, are electrons gonna flow towards it?
No.
No, because they're also negative. So the point of the salt bridge is to keep the neutrality of the cells so that the electrons can continue to flow. So the salt bridge is full of K plus and NO3 minus. So as these positives leave, the positives in the salt bridge flow into that solution. This side is having the opposite problem in that it's becoming too positively charged because of all the stuff that's dissolving. And so the NO3 in this side, or the NO3 travels over to this side to keep it neutral. Questions on that?
Stop.
If the NO2 and the K plus goes into the water, why does the salt bridge not dissolve?
Say that one more time.
So you know how the K plus is making one side not too negative?
Yeah.
How does it do that without dissolving?
Oh, good question. So the salt bridge isn't made of these things. The salt bridge is a surface that those things travel on. So like mine up here is a piece of paper that I soaked in potassium nitrate.
Okay.
Does that make sense? So it has potassium nitrate and they can flow across it, and but the paper will stay. So, great question though, Isaac. Yeah.
So usually with these reactions, does the salt bridge like run out of salt before the zinc or copper runs out of zinc and copper?
Good question. So that's, Gavin kind of brought this up too. So those are one of the many reasons why a battery dies, right? Is either this electrode gets all gone, the salt bridge. Now the thing about a salt bridge is technically once, like there's a bunch of nitrate over here too, right? Because it's in a zinc nitrate solution. So the nitrate that's over here can flow.
That's not our thing.
Oh, I said that backwards. The excess zinc that's being dissolving could flow across. So I'd say normally it's probably not the salt bridge, but if your salt bridge fails, then your battery's not going to work anymore. So, yeah, good point. Okay, turn to your table, buddy, and play a game of rock, paper, scissors. That's 2 out of 3.
Do I want to win or lose?
I think
Game, always so long.
Rock, paper,
Rock,
played last time.
You waited, Peter.
Rock, paper, scissors, shoot. I don't know if I
Okay,
won
now
or
play game.
not. Rock, paper, scissors, shoot.
Okay, play game. So I have to do a 3-way over there. No pressure. Oh my goodness.
I thought it was gonna, like, slowly get faster.
How is that?
Okay, raise your hand if you're the winner. Raise your hand if you're the winner. Okay, if you are the winner, you're gonna take 90 seconds
Yes, I knew it.
and explain to your partner this whole process again. Ready, set, go. Walk them through it.
So,
But laugh does it get too fast?
copper on one side,
Yeah. Got to press it a little bit.
so then the wire.
Explain to me this salt bridge thing.
And the electrons go across the bridge in reaction. And so then they take this side and the K plus to this side to make it not too negative, and the NO3 goes to this side to make it not.
is what you saw type of relationship. Building yourself up by pushing each other down and everything else like that. I'm very sorry. I actually prefer the hydraulic unit, but if it is,
So funny.
No, dissolve in it. Why does it dissolve in it?
So, yeah, so it's what you said, like the negatives are more negative, so like the positives are attracted.
Yeah,
It's a
that's what I was thinking.
neutral. And then there's more negatives.
And the NO3
Oh, yeah.
and the copper getting
accurate
canceled.
representation of tape.
But then why would you need the K?
Finish up your explanation in the next 10 seconds.
Yeah. So maybe we should ask.
K plus is the shortest trial.
That's a pretty good drawing.
Yeah, I'd say that's pretty accurate
Pretty good?
example right there.
Oh.
Not that right there. See it?
Yeah. I have like a mohawk on this side of my head,
Uh-huh.
right here, according to this drawing.
Yeah, and I'm completely accurate in everything I do. Just look at my test scores.
Oh.
Okay, any new questions after walking through it again that have come up? Now, yes, Isaac.
Why does the zinc dissolve in the water?
Because it's losing its electrons. And so when something becomes, so originally it's solid, right?
Yeah.
When it loses its electrons and becomes positively charged, ions only exist in aqueous solution. So there's no such thing as solid Zn2+.
Okay.
Does that answer your question?
And then the CO2 plus gains their electrons, so it goes into a solid.
Yes. Yep.
No.
Taylor.
So, could the water get saturated and then like the thing would stop?
Yes.
Okay.
Yep, so that's another problem that can happen too. Now the AP people love to have you draw these things at the molecular level, which is why I spent doing it right now. Almost every year, not normally like the whole thing, but normally there's some part of it they're going to ask you about in terms of molecular level, like the salt bridge, like draw what's going on at the salt bridge, which direction the positive and negatives are going, which one's getting smaller, which one's getting bigger. So really understanding this concept at the molecular level, hopefully it should all just make sense too, because it is a very connected process. So, okay, let's go through and we're just going to fill in the bottom, which is, once again, the same thing again, but just to get it down in words so we have it.
Are we ever going to watch that reaction?
Oh, I need to plug it in. It's not super exciting because it's not fast, but I can link it up now. Let me make sure my salt bridge is okay.
Hey buddy, are you okay? How are you feeling?
How fast?
Oh, I heard the best thing.
Like, will we be able to see the results?
The electrons was a little different, but not much. So,
You should leave it in until next class.
just let it run all weekend.
What if the whole liquid just became solid?
So you practically just need a battery.
Yeah.
So you can just make batteries for your own thing.
Good question. No. So it's interesting because actually what also can work as a salt bridge actually is your own fingers.
Do it, I dare you.
And a lot of people are like, why are you going to get shocked? Where are the electrons flowing?
Your one finger to the
Yeah,
other.
they're flowing through the wire, right? So it just, the salt would just be traveling along your hand, right?
Wait, that'd be so cool.
Um,
I know Taylor.
My wire's being a little,
You know how it would feel if you got shocked?
keeps
I
fluctuating.
feel like this.
It would be quite
Oh,
shocking.
wow.
Can you see, it's like, my wires are being
I am
trippy today, so it's
ashamed
not
to be
holding
your friend
constant.
right now.
Can you guys see the numbers popping up there every so often?
Oh, I saw 0.02.
Yeah, once again,
Negative
something's off with my wires. But that's showing the voltage that's being produced as it happens. So I'll let it sit throughout class, and then I'll kind of show you the electrodes at the end, and we might see a little bit of change. It's not super fast, but I'll kind of let that go. So this once again, oh, one other thing we forgot that is on here is the word anode and cathode, which should be familiar when you talk about batteries. Okay, anode is the location where oxidation happens. So on your diagram, if you want to label, which one would be our anode?
Wait, you got your anion and your cation. Cation is positive and
Where
anion is
oxidation
negative.
occurs,
No,
oxidizing
it's
means
So the zinc is your anode.
Okay.
Yeah. The The other way is electrons always flow from the anode to the cathode, is the way they flow, at least in a galvanic cell. Okay? A phrase kind of like oil rig that I learned in college, if it helps, is you can remember anox and red cat. So the anode is where oxidation happens. Reduction is at the cathode.
An ox, red cat.
Purple moose.
On a
I'm sure you come up with a story about that, right?
So,
Oh,
there was
so
an ox.
And then they got up to an oil rig.
They were such great friends. And one day,
And the ox kept giving stuff to the cat, and the cat never gave anything to the ox. And the cat was a jerk.
oh my gosh,
You really
you're
could
making
write
me
a children's book about this.
Yeah, and then in 30 years, we'll all call you racist or something.
Not true. I swear.
Okay, we're not going there.
No?
Okay.
Okay, sorry, my bad.
Okay, so a few other notes about the salt bridge, just have it in writing. Okay, so the salt bridge job is to keep the solutions neutral, right, so that the electrons can continue to flow. If they don't flow, then the reaction will stop. Once again, it just provides a place for them to migrate the positive and the negatives to the different components. It can be any electrolyte solution, just as long as those electrolytes won't react with what you're doing your battery with. And then the biggest thing is that in a voltaic cell, these are thermodynamically favored. A battery is thermodynamically favored, otherwise it wouldn't be a battery, right? Because that means you have to put energy into it.
A reverse battery.
A reverse battery.
It's like
It's when you suck up the sun, you just threw tons of those reverse
Gavin, you
batteries.
just stole my next question.
Oh, I'm so sorry.
No, I perfect lead in. Don't say it out loud, but now key it in your head. Can you explain to me how a rechargeable battery works?
Oh, this one.
Don't say it out loud, but knowing what we know now. Move, travel, something like that? The last one. The electrons flow, probably flow is a better word. Flow from the anode to the cathode.
Low.
Which one?
The bottom one. The next bottom one is migrate. That's migrate.
This one's migrate?
No, the middle one.
This one's
migrate.
Okay, don't say it out loud. Before we jump in, I'll explain this in a second. No, the first paragraph disappeared. Okay, but before you do, I want to make sure, because this will help us in our understanding. Knowing what you know, if this is a battery, how does a rechargeable battery work? Don't say it out loud. At the molecular level.
I don't think that's how a rechargeable battery. Or Duracell. You plug Duracell at the battery, and it's like, alright, I'm ready to go again. Imagine a voice charged battery. You just scream at the battery, and it slowly charges.
Wow.
Your anger turns into.
Okay, any ideas how a rechargeable battery works? Isaac, you have an idea. Let's hear it.
Maybe. So, what if it just has it where it holds, makes it way negative spot? Like it just holds a lot of negative electrons, and so then when you charge it, put more negative in it, but then when it'll release negative electrons.
Kinda. How's my face for that? You're on the right track. The simple idea, once again, batteries are a lot more complicated. They can be more complicated than this, but there's the basic idea. So as this is working, right, the electrons are flowing from the zinc to the copper. If this was a rechargeable battery, when I plug it into the wall, that power then sends the electrons back.
Oh, it plugs into the copper and moves it to the zinc.
It uses energy to force them the other direction, and then you have it again.
Oh, so it becomes the opposite of the thermodynamic.
So,
Yes.
So charging batteries are cold.
So that's where even rechargeable batteries can eventually not work anymore, because various things can fail, right? Either the salt bridge fails, or it's not 100% efficient, and so slowly over time you're not building up as much. So yeah, that's why we don't have a perfect rechargeable battery that never dies, right? So
you could
yeah, good
recharge
point.
So, do rechargeable batteries add electrons to the battery? Because when you use a battery, it uses up the electrons?
Yes. So electricity is just electrons, right? And so when you plug it into the outlet, that electricity, those electrons then flow and go back.
Why is your pencil so annoying?
So yeah, no, great point. And yeah, the electrons are being in a sense like used up, right?
That's my question.
So
What is
So in terms of like a car battery,
Yeah.
I'm trying to think in terms of what part of this does the acid serve?
I don't think so.
I don't know, I have to think about that, Winston. I've never thought about it in terms of like, what piece of this is it, what function is it serving? It is, yeah, no, it's already in there, yeah. It might be serving as one of the solutions. Maybe it works more effectively. I don't know, I'll have to think about that. Okay, the first paragraph of this got deleted or something, so I'm just gonna tell you what to fill in. So, here's what it says right here. Okay, electrochemistry is the study of redox reactions that occur within electrochemical cells. The reactions are either thermodynamically favored, meaning they have positive voltage, right? That's like how many volts it puts out, like a 9-volt battery. Okay, or it's unfavored, meaning they have a negative voltage, meaning they won't happen without volts being put in, and those require an externally applied potential. So if something is unfavored, meaning it has negative voltage, that means you have to put in volts to make it happen. Now let's talk about that flow of electrons. So we talked about in our example that the electrons just go from zinc to copper. I don't have to do anything besides set it up, it just happens. The reason why it just happens is because it's all about the transition of potential energy, traveling from high energy to low energy. I don't know, that was kind of creepy.
What?
Anyone see that move?
Dude, white cup, like, she's just like standing and all of a sudden this white cup's just like, zoom, it just moves across the table.
It's coming for your soul.
It was a little weird. I mean, it's really light, so I'm hoping it's just a gust of wind, but
If it goes,
it looks weird.
Just walk in the
I
past.
can rewatch the video on that.
The slow-mo replay. Somebody play that back.
So with this reaction that we just did, it has a voltage of 1.1. Now, with this idea, let's learn how we can calculate this equation. So E cell represents how much energy is produced or required for these electrochemistry processes. Now this formula I'm going to write is not on your formula sheet, make note of that. This is not on your formula sheet, but it's a very straight up equation. To calculate the total energy that gets released, we just combine the voltage of the reduction and the voltage of the oxidation.
Oh.
Just add them together.
Is the dot thing the standard conditions?
Yes, thanks Gavin for bringing that up. So this means we're under standard conditions, which for our cells, an important note.
eventually the ox and the cat both go to prison.
Wait,
One ox plus the one
Oh,
cat equals one
cell.
cell.
I was like,
Oh.
why are they different from the children's book?
Yeah, see, now you'll get in real trouble now.
Well, as it teaches them to never be like the stupid cat because a jerk.
You're on drugs or something.
Okay, this right here is an example of some reduction potential. So scientists, like a lot of things we do, have calculated the potential of all these different reactions. Your book has pages of them. This is just a small glimpse of some of them.
Those guys are just like the best. They're like, you know, I don't want anyone else to ever have to do this, so we're gonna do it for them.
Pretty much.
Those are
Now,
important, dude.
what they did decide though, for simplicity, is rather than making tables of reduction and tables of oxidation, they really only have tables of reduction. The reason being is oxidation just flips the sign. So really the only tricky part to use in this equation is just making sure you identify which one needs to flip in sign. Now what this table shows us is the more positive the value is, so it goes, notice it gets more negative as we go down, the more likely it is to stay as written, meaning it's going to be reduced. So what this does is if I don't know what's going to be reduced and what's going to be oxidized, by looking at their values, you can identify that. So in that box up there, write more likely reduced. And then these ones are more likely oxidized.
Oh, wait, we're about to,
You got it, Taylor.
she's right on the side. So.
Voltaic.
Okay. So no matter what I put lithium with, lithium always gets oxidized. And same thing, fluorine always gets reduced.
Sure, if you put fluorine in lithium, all of a sudden they switch
You
roles.
get a really good battery. Maybe
Well,
that's
you
why we
know
have
what
lithium ion
batteries,
batteries.
you
Sarah.
have. You know, makes sense now, like, that's why they're lithium, that makes sense. You know what's weird, lithium is only weighs like, it's like the third element.
Uh-huh.
It feels like it should be more than that, you know, it feels like it should be later on,
Why?
just because, you know?
Oh, just feels like it should.
It feels
Just
like.
Come on! It's a science book, dude. You all know this?
Maybe I just had a feeling that it should be somewhere else.
You're like, psychic over here.
Okay, so the greater that E value, the greater that thing will stay as a reduction versus flipping and becoming oxidation. Okay? Okay, we have 4 minutes. 3 minutes.
Yeah, 3 minutes.
Max, I voted for you.
If you do this problem,
Max, I'm sorry, but I haven't voted yet.
okay,
I don't think you're gonna
really
lose
worried.
though, Max, I'm not too worried.
Yeah, I'm not too
You
worried.
got some tough
I
competition.
think you got this one in the bag.
It's funny how there, for some other options, there's only one person.
okay, we're gonna stop there because I don't want to get halfway through solving this and then the bell ring on us. So I'll pass out your practice set number 2 and I'll tell you which ones to hold off on for now.
No respect.
You know that if you put fruit,
Okay, so for tonight's homework for you guys, you only need to do the front page. Okay? You only need to do the front page for now. Because we didn't get a practice the equation I just showed you, which is the whole back page. So I won't expect you to do it yet. Okay? And then, no, you do have some pages of reading to go along with it, but not too much, hopefully. So.
Oh, and Winston, you have to take the test.
Yeah.
Yeah.
I'll take